Good morning, ladies and gentlemen. We are now about to start today's lecture. Today we invited Rouhi from TU Delft of the Netherlands. Rouhi is an associate professor of reservoir engineering at Delft University of Technology and a senior reservoir engineer with Shell. His research interests include flow in power media, CO2 sequestration, underground energy storage, life cycle assessment of energy system, and enhanced oil recovery methods. He is the recipient of 2018 SP Reservoir Description and Dynamic Regional Award. Rouhi is the executive editor of Journal of Petrol Science and Engineering, and he is the editorial board member for scientific reports and MDPI Energy Journals. He holds a PhD and MSc degrees in reservoir engineering from TU Delft and BSc degree in chemical engineering from Tehran Polytechnics. The topic of Rouhi's lecture is thermodynamic efficiency limiter of the subsurface energy production and storage system. Welcome, Rouhi.
Yeah. Yeah, thank you, Mr. Chairman. And before I start, I'd like to apologize for my voice. It's not for a party, it's just a bit of cold. And I'd like to thank InterPore for inviting me to, let's say, share our findings with you. And next, I'd like to acknowledge, especially to people, Dr. Eftekhari, who is sitting here, and also my PhD supervisor and later collaborator, Dr. Browning, who basically we went through a big journey to develop this methodology to assess energy efficiency and CO2 intensity of energy systems. And I also would like to acknowledge my PhD student, Aga Bagirov, who basically did some of the analysis for the hydrogen story. And yes. So one of my favorite books is called Hot, Flat, and Crowded. And obviously hot stands for global warming. Flat, at least, the book was from basically before presidency of Donald Trump and Brexit and the war. So it stands basically for globalization. And crowded is obviously the population growth that we have. So what we know is that at least based on the projections, the population of the Earth will by 2035 will reach to 8.8 billion. It will plateau around 11 billion statistically, but what it shows is that with the increase of population and also the rise of some emerging economy powers like China and India, the good news is that we will lift a lot of people from basically poverty to middle class families. But with that comes a lot of energy demand, right? So because we will have basically a lot of people on Earth, but also a lot of people who will need much more energy than they are consuming now. And this energy has to come from somewhere, right? So there are some projections, and I got some figures from BP's review, and unfortunately they stopped doing this amazing job that they were doing I think since 2 years ago. But what it shows is that we will, so most of our energy, unfortunately, or for what reason, has to still come from fossil fuels, at least by 2030-35. And let me find out the laser instead of that, yes. And what we see is that the share of course, coal and oil will come down as we go. But the share of gas, natural gas, will go up. And by that, the share of also renewables will go up. And renewables includes basically hydropower, nuclear power, and and other sources of energy. So the message is that we will still, at least for a short time of a period, at least by 2035-40, we will be heavily relying on fossil fuels. So we have to kind of find ways to produce it cleaner and also to create the mess that, or the carbon that it will emit. So that's why we have the topic of energy transition, and it has been like, basically we have seen many great slides or presentations in this conference. So we will have energy transition, and during this energy transition, the key thing will be to decarbonize the energy sources that we have. And that can be done in two ways, what I call preventive methods, which means that we improve energy efficiency of the systems, we make them cleaner, we produce everything cleaner. So basically, we emit much less CO2 to the atmosphere than we do. But then that will not be enough to meet basically this 1.5 or 2 degrees Celsius temperature rise limit, so we have to do some negative emission technologies, use them. And that is when the mitigation methods come. And we have kind of, let's say, CCS technologies that we are working on now. And the CCS technologies, we have CO2 capture from high concentration sources like power plants, or we have like, let's say, direct air capture, which is low concentration sources, and we can locally capture CO2 and store it. So but basically, we need to, during energy transition, I put this should on purpose in italic, and that's actually a question that we have to, or replace these basically fossil fuels by cleaner sources of energy. But I would argue that energy transition there are two things for that, right? So one is that we will come later to the topic of energy diversification, but the second thing will be that we need to have consistent methods of evaluating energy sources. And that means that if somebody comes and says, I have a basically technology based on renewable electricity, that doesn't mean necessarily that it's a clean source of energy. So we need to have methods to evaluate these technologies. And so if some source of energy is from, let's say, natural gas or other sources, if you can clean it with CCS, for example, you can make it cleaner. And I will actually go with the numbers, because that's why I am here to talk about it. So usually we use cost, MPV, or other, let's say, economic terminologies as, let's say, ranking for a lot of processes and projects, right? But here, what I'm going to do is I'm going to show that for us, for energy transition, actually, the CO2 intensity or gram of CO2 per megajoule of energy, and energy could be in the form of electricity, heat, or whatever, should be seen as basically the indicator of sustainability or cleanness of that fossil fuels. And the whole purpose of energy transition is about reducing this number, regardless of the source of the energy. And then the whole topic will be that. So if you look at this, and this is again by the PhD work of Ehsan that I adapted it a bit later. So if you look at this diagram, every process has an efficiency with basic, and you can optimize it based on any parameter, right? Let's assume that this is a hydrogen storage project, and you have hydrogen, let's say, extraction recovery factor. And this could be, I don't know, any parameter like injection rate, withdrawal rate, or composition, everything. So for any kind of system, there is an optimum point, right? So you could get maximum efficiency of that system with optimizing the parameter, and you will get that. And for any system, we have an upper limit of recovery factors. For example, if I do hydrogen storage, I cannot get more than 100% of that hydrogen out of it, unless I have also reactions and generations. But let's assume there is no reaction. So there is an upper limit for these processes, and then when we don't spend any energy to basically inject, produce, and everything, then that is one. But unfortunately, that's not the case with theoretical efficiency, right? Because second law of thermodynamics, basically, or entropy generation, does not allow that. So we have basically theoretical recovery factor efficiency for any system. But now that is only for reversible processes. And when you have irreversibility in the system and entropy generation, that there is also distance between what we call practical recovery factor or efficiency than theoretical. And that is actually the whole thing about also, let's say, energy transition, in my opinion, to basically reduce the gap between theoretical and practical process efficiencies by improving the efficiencies of whatever we have, the drives, the power plants, etc. But then, if we want to be carbon neutral, we have to actually spend more energy to basically capture the CO2 that we have emitted and store it or utilize it as feedstock in other processes. And that's what I call it, just basically the gap between practical efficiency and carbon neutral efficiency as sustainability cost. And that sustainability comes with cost that is translated into energy and also of monetary, let's say, numbers, right? So and nobody, basically, we know that. So it comes with energy and money cost. So what I'm going to present, actually, again, we have developed this framework based on exergy analysis, it's life cycle assessment. Like any life cycle assessment approach, for energy system, we identify the main components, subsystems. We don't go into detail of, okay, what is being used and stuff. It's just very, like I said, high level, but more really important processes that we have. Then you define your system, your boundaries. You say, okay, what kind of work I will spend, like energy in basically, for example, CCS, we have to capture it, compress it, transport it, then recompress it, inject it, and all these pumps and compressors, they consume energy. And with energy comes also CO2 emission. So we can quantify that. Then we know what kind of, let's say, output we have. In CCS, unfortunately, we don't get any useful energy out. It's all negative energy that we will consume. With hydrogen, for example, we will also get energy out. So then we do exergy analysis, and then we analyze the output. And this is great approach, because once you visualize the subsystems and you see which basically component of your system consumes most of the energy, and then you can try to optimize it, and then, like I said, you can reduce the practical and theoretical recovery efficiency that we had from the previous slide. But what is exergy? Exergy is actually nothing more than basically the translation of energy into basically from second law of thermodynamics. It's useful amount of work that you can get from stream of money, basically. That's the whole thing. It's kind of a money exchange that you consume. Basically, you have $100, you convert it to euro, you lose back, and then you convert the same euro to dollar, you are losing a lot in between the transactions, right? Because some people get money out of you, and that is what it is. Any useful work that you will get out of your energy that you have will not be exactly equal to what you have spent. And the exergy of a substance is a function of many things. We have kinetic exergy, potential and physical exergy, and chemical exergy of fuels we could usually consider as their lower heat value. And they are basically dependent on pressure, temperature, and composition of the current state and the dead state, like this guy, because at dead state there is no useful energy that can come out of any energy stream. So now, based on this, let's assume that we have this we developed initially for oil recovery, basically the technology. So for any recovery mechanism that we had this oil recovery factor versus per volume of injectant, and I will give an example of CO2 injection. And then so basically you would have a recovery factor from going from 0 to theoretically 1. We will never reach there, but it goes from 0 to X. And then based on that, we defined a parameter, we call it sustainability indicator, exergy recovery factor. And exergy recovery factor is the amount of energy you return minus the amount of energy or exergy that you invest divided by exergy of the fuel that is in place. And that exergy recovery factor number can go to negative. So Ehsan used to joke that while basically exergy recovery factor could be between 1 and minus infinity. So there is a limit of 1 for happiness, but misery doesn't have any limits. So that's the whole thing. The bottom is really deep. So another indicator is exergy return on exergy investment, and that is simply the exergy that you return and then exergy that you invest. And we invented it because then suddenly you can become happy, because then it is between 0 and plus infinity, because that is happier a bit, right? So let's now basically, okay, yeah, two concepts. So exergy zero time is when you basically actually the amount of energy that you will spend for the process will be much more than energy that you will get. And that is when actually it becomes equal, but below that it becomes negative. So that is not actually thermodynamically sustainable because you are investing more energy that you can get from the same process. And that's not thermodynamically acceptable. From economic point of view, something could be acceptable. From policy point of view, completely acceptable, but not from thermodynamic perspective. And then, and also these recovery factors, exergy recovery factor, I will not use that much. So I am going to show some examples of basically the methodology. So let's start with the simplest case of CCS, carbon capture and storage. Very simple. We take fossil fuels, gas and oil or coal, we take it, we combust it, we will get heat, power plant, and then we will get electricity out. So to make this electricity now to basically zero carbon electricity or zero emission electricity, you also have to now, basically, we have to capture the CO2 that comes from flue gas itself. That is already very energy intensive, so it is thermodynamic exergy of separation is this one. Depends on the composition of basically CO2 in the gas stream, but the efficiency of that process is also very low. And then once you capture that CO2, you have to compress it. Usually compression is done in the capture side, and then you have to spend energy, the same electricity that you have gotten from basically power plant to transport it, and the same electricity you have to basically compress it again in the storage side and then this electricity that you are consuming basically also has some CO2 emission. So if you want to actually be very carbon zero, so you are spending energy, but then you are again producing CO2. So you have to capture that CO2, but it goes on and on, right? So it's never end. So these capture efficiencies, there are like in the order of 90%. So this is the only economic graph that I am showing, right? So basically, and the reason is that most of the work, again, that was done by us, and last year so because 2021 and 2, they are really great examples of low gas price and very high gas price, right? So, and that shows basically the sensitivity of these CCS technologies on the gas or the basically electricity price of the market. So the exergy of separation is, like I showed, is like 5.5 megajoule per kilogram or 1.5 kilowatt hour per kilogram of CO2. And so if you plug in the numbers, basically July 2021, before the war in basically between Russia and Ukraine, you had very cheap gas. And then after the war, the prices spiked, right? So if you put that number, this is what happens with the CCS technology just for the cost of the capture. So you have to add actually additional numbers on other activities that can be done. And you can see that actually for very favorable, actually the minimum price could be for gas, let's say between 20, and it can go up to 150, 40. And like I said, if you can add other numbers, it can be expensive. So this shows again the dependency of what we do as engineers on actually some things that we cannot control, because we like to be zero. And ideally, actually, like I said, we should not use the electricity that comes from the same power plant to do the capture, CO2 capture thing. So for CO2 or CCS to be actually really clean technology, this electricity should come also from a low carbon source. Otherwise, like I said, it will be endless story, and we will struggle a lot with cleaning the carbon that we emitted. So CO2 enhanced oil recovery, another great process that people say, okay, it's a means of storing CO2, but let's look at the numbers. Again, I have to capture CO2, initially compress it, take it to transport it, take it to compressor, then I have to inject it to the oil reservoir, and then the oil comes out. I have to separate methane from basically CO2, which is another energy intensive process, and then transport it, and I need to have the water for mobility control, and then it goes on and on. So if I look at this again, so this figure is based on 3 recovery factors that typically we have in the industry. Actually, the worst case scenario, the base case, or the best case scenario, right? And actually, you can see that there's a limit to this process as well. So after some time, even though most of these projects are economically viable because of the price of the oil or other stuff, but thermodynamically, they can become not sustainable because, again, I have spent more energy during the process of capture, transportation, and everything to bring the CO2 to the site, and the amount of oil, energy that I have gotten from oil and gas, it's not enough to compensate for that. Again, a great example of things can be economic, but not thermodynamically sustainable. So to make it more interesting, this graph I like a lot because it tells a lot. So 1 barrel of oil, basically if you burn it, you will produce about 400 kilograms of CO2. And if you want to continue basically, and the y-axis here is mass utilization factor, and in industry they call it as amount of oil, barrels of oil that you can get for ton of CO2 that you inject. And for all the projects that is in the industry, the best ones, they have had 4 barrels of oil per ton, but on average, it's actually 2, right? So let's focus on the 2. So if I use CO2, which by the way, 90% of the CO2 your projects, they are not using captured CO2, they are using CO2 from geological formations. And we see the reason, because energetically, you lose a lot of energy negative, and that's why they don't capture and transport, they just produce it from geological formation, and then that doesn't contribute anything to the climate change, because that CO2 better stay in the underground. But that is why it is the efficiency of this process is quite high, it's more than 90%, but the CO2 emission that comes with it is also very high, because you see the barrel of oil produces 450, and the process produces between 150 to 200 kilograms per barrel. But if you now want to make that EOR projects from use anthropogenic CO2, then of course you get 80% reduction on CO2 intensity of that oil, which is great. Suddenly I go from 600 kilograms of CO2 per barrel of oil to 100, which is great, but that comes with a lot of energetic cost. So my efficiency drops from about 85, 90 to only 50%. So it means that I have to actually consume more than 30-40% of my energy that I get from oil to clean up the mess or the carbon emission that it has had. So let's move to some basically renewable stories, right? So we heard some great talks about underground biomethanation process. It is a process that is in the context of hydrogen production. That the idea is that the hydrogen that comes from renewable electricity, we combine it with CO2, we co-inject it, and we create synthetic methane in the reservoir. So this analysis, we are going to basically assume 100% conversion efficiency, everything great, so basically the ideal case that can happen. And then from this reaction, for every kilogram of methane that I produce, I will need about 2.7, 2.8 kilogram of CO2 and half a kilogram of methane. So I define my boundary, and basically water electrolysis, hydrogen, and then the methane goes power plant. We clean the methane and bring it back. And then some assumptions, the numbers are in the paper because I am looking at my time, and time is flying when you are here, so it's sorry about that. So, and some numbers, the cost of compression of hydrogen, transportation, and also the cost of production of hydrogen, right? So this is hydrogen and energy intensity. We also heard a lot. It's 120 megajoule per kilogram, and you can see that already we have lost there, right? So it is 180 megajoule of electricity we have to spend to produce minimum the hydrogen that we will get maximum 120 megajoule of electricity later if everything goes okay with 100% efficiency. So with some stuff, basically this is the efficiency of the process. Of course, natural gas plus CCS in this case wins because it's a primary fuel. We have not spent any energy to produce it, so it has been basically done there. And this process, because we have spent a lot of energy on hydrogen and CO2, the efficiency is not great. But that is, again, in the energy transition, this is not a big issue because electricity will be abundant, hopefully, and we can afford to lose electricity and energy if this figure or basically this figure makes sense. So basically the CO2 intensity of the process is better. So I'm comparing here biomethanation for electricity and heat route with basically methane plus CCS, and also for electricity and heat, and direct use of actually green hydrogen. And as you can see, basically this biomethanation process has a very big CO2 intensity. So if I utilize actually my hydrogen directly, yes, I'll finish it in 10 minutes. Sorry. But basically, to make it short, biomethanation is basically the fuel that you will get, energy you will get. It is not making sense in terms of intensity. But there is one positive thing, that during energy transition, we can use existing natural gas infrastructure to produce this energy. And also, if you want to do it, surface sense makes more sense than subsurface, even in the scale of it. But hydrogen storage, subsurface hydrogen storage, again, a lot of processes that comes in: renewable electricity, hydrogen production, compression, transportation, recompression to high pressures of reservoir, and then back production. Then you have to separate the methane. You either re-inject, take it to power plant, a lot of options, and then you transport. And with hydrogen, the great deal in Europe is about purification. We cannot actually get less than 98% purity to the market, because that is what the market needs. And this, again, purification is super energetically super expensive, because PSAs are very energy intensive. So if I do basically collective, these different hydrogen basically production methods, they have a lot of, the energies are high, they come with CO2 footprint, and I am going to talk about steam methane reforming and another process. Again, we have calculated this stuff. I can share the numbers. A lot of energy that is consumed a lot during the process, but more importantly, we have for blue hydrogen the fugitive leaks of methane. With methane is unfortunately a lot of leakage, minimum 1%, and we have done some analysis on the percentage, and the global warming potential of hydrogen, methane is 86 in the 20-year period of time. And hydrogen itself, let's not forget about it, it's also a global warming gas. With actually and it's a very small molecule. During transportation, it will be leaked, and it is leaked, and it can be 1 to 10%. And this hydrogen has global warming potential of around 8, actually, 8 times more dangerous to basically atmosphere than CO2 itself. So to make the story short, the efficiencies are more or less for all the technologies that we looked into. SMR plus CCS is a bit less, because we spend a lot of energy again during CCS, make the gray hydrogen blue hydrogen, and the ATR plus CCS again. And this partial oxidation is a bit better, because during production hydrogen, that hydrogen comes with high pressure, so you don't need to inject it, basically compress it a lot. But this is my most important maybe slide for this process. And again, this is the SMR gray, blue one, very large basically CO2 intensity. And then this is natural gas plus CCS, including actually methane emission or methane leak that you have. And it compares good with this is the green hydrogen using wind power. So, and then the subsurface element of it, of course, contributes to 25% of CO2 intensity. But what it shows is that the surface elements, the hydrogen production, compression, and transportation, basically emits most of the CO2 rather than the subsurface. So I hope, so for me, basically, energy transition is about diversifying our energy portfolio. We have to have basically different sources, and let's face it, fossil fuels are so limited. Even if we don't think about now, 50 years later, we have to think about solution. So it's about diversifying our energy sources and making them cleaner, and we don't have to exclude basically some technologies or some sources because of the perception. And I end this presentation with a quote from my PhD supervisor, Dr. Browning. We are engineers, and our greatest tool is numbers. What basically politicians do with numbers is not our business, but we have to show the numbers, and the numbers are what I showed, with the assumptions that I have made. Thank you.
Thank you, Rouhi, for giving us a wonderful lecture. We have a few time for discuss
Sorry about that. So
everyone to ask question. One or two? Come.
Yes, thank you for your interesting talk. How close is the exergy analysis to the classical life cycle analysis? Because in the life cycle analysis, you take into account the energy needed to build the infrastructure. Is this correct? Or?
no, we have not actually. That's
So,
great
because
question.
if you include this in addition, then
The numbers will be a bit,
change the numbers. Yeah.
they will make the number a bit worse, but it will not change much because the capex is or the capex, I call it the energy capex, is not basically that great compared to the numbers that come during the project itself. But I have not included actually those manufacturing costs yet in the process. Okay. Yeah, but it will increase the numbers especially. So.
Okay, due to time constraints, we will end today's lecture. Thank you again, Rouhi.
No, thanks.
Now, next program is learn about TE scan.
Hello everyone, my name is Marijn Boone. I'm the product manager for MicroCT at Tescan. At Tescan we produce X-ray microscopes or microCTs, but we also produce SEMs and TEMs and FIP SEMs. I'm going to mainly focus about the microCT solutions. What we can do with our microCTs is quite versatile because we can scan objects up to 1 meter tall and reach resolutions down to 600 nanometers. But what all our systems have in common is that they are fast, versatile microCT systems that allow continuous dynamic imaging. Why dynamic imaging? Because we want to enable to visualize processes as they are happening. Here you see an example of particle tracking, and this is a scan at 3 seconds for 1 rotation, so it's really fast imaging, and it allows us to follow how particles are moving through a fluid. A second example is a capillary uptake experiment in a pharmaceutical tablet. So this is 4 seconds per scan, and it really allows you to monitor how the front is moving through the pharmaceutical tablet. What is the problem with dynamic imaging? Well, it's not really our problem. We enable all the tools to make it easy for you to do that imaging, but usually the setup is quite hard. I have seen here examples of setups with hydrogen at very high pressure, very high temperature. Setting something up like that is extremely complicated, as most of you most likely know. We also have a system where the sample doesn't rotate, but the X-ray source and detector rotate around the sample. And this really makes it easy for scanning very complex setup and monitoring what is happening inside your sample. If you think, okay, great, I want to do some fast imaging, but I don't have budget for a system, then I have really great news for you, actually. Because we are having a call for proposals, and this is a week of beam time at our facilities in Ghent, Belgium, where you have access to all the systems, the dynamic systems, and also to the technical team present there and the application team. So if you would want to do some scans or want to do some experiments, please submit a proposal. Either come by the booth, send me an email, and I can give you more information on how to apply for that. Thanks a lot.
Yeah, thank you for your introduction. We have just a moment. We have 2 minutes. Everyone ask a question.
If there are questions,
Yeah. Everyone, any question?
If there are any questions, please come by the booth. And,
Thank you.
Thank you.
Okay. We close this program. Thank you.